Okay, ready to start?
Yes.
Okay, hi everyone. Today I'm going to present you a project that's on the topic of meta-learning. The title is Learning the Order of Learning, and we'll explain what that means in just a second. So this is the outline of the talk. So firstly, I'll give some definitions of what is learning order. Can humans learn the order of learning? And then can we do that with a machine? So what is a learning order? That's the essential question. Suppose I give you two arbitrary models of the same modality. So that could be, for example, image classification, it could be LLMs, it could be any arbitrary model, and I tell you that one model has a higher accuracy than another, right? So now, here comes the question, in what order do they learn? What do I mean by that? Well, there are a few possibilities. So it could be that the higher accuracy model here gets the same examples correct that the lower accuracy model gets correct, plus some additional ones. That we would call the matched order learning hypothesis. There's also another possibility, which is the model that's higher accuracy essentially gets correct the opposite of what the model with the lower accuracy gets correct. It just gets more examples correct. And then there's also the possibility of a random order. This is all work done by David that we're expanding upon now. Just shout out to David over there. So which of those is the case? Turns out the matched order hypothesis seems to hold regardless of modality, which is quite interesting. So this is the ImageNet validation set. As just to explain, so here on the y-axis is essentially the bottom is like the worst model on ImageNet. These are just arbitrary models. On the top is the best model on ImageNet. And as you can see, the best model gets correct basically the same examples that the worst model gets correct, plus some additional ones. So it's not random and it's not opposite. And this seems to hold regardless of modality, of course to various degrees. So with image classification, it's clear. With LLMs and some other data sets, it's less clear, but the pattern is evident that learning follows an order on the macro level. So can humans predict image difficulty or learning order? So suppose that I gave you these two images of an apple, right? I took one of the images from the lower half of the ImageNet dataset and another image from the upper half of the ImageNet dataset, which roughly corresponds to the difficulty of the images, right? So now I have a question for you guys. I want to know which image came from which half of the data set. So if you think the image on the left side is from the lower half, which is the easier images, so if you think the image on the left is easier than the image on the right, please raise your hand. Okay, nobody, that's good. And then the image on the right, of course, follows that. That must be the easier one. So indeed, that's correct. So actually, indeed, you see that humans can do this. We can tell which image is more difficult. It's that image, right? So can machines do this? Is the next question. And this was inspired a lot by Manganese research. So she essentially did this on classification. She wanted to predict whether a model is going to get something correct or not. We're doing something slightly different, but the inspiration came from Manganese. So shout out to Manganese here. So here's the first thing that I tried. I trained 500 models. Vision transformers, ResNets, clips, all sorts of things with grid search, tried all sorts of hyperparameters. And we find that you can get quite a bit above chance if you try to distinguish if an image came from the lower half or the upper half of the data set. Chance is obviously 50%, so we do quite a bit better than that, which is interesting. I tried the same thing, but instead of classifying just two halves of the ImageNet dataset, I classify into 5 categories. So I just split the entire spectrum into 5 instead of into 2. And again, we get accuracy that's above chance. There's a big problem, however, which Mangan pointed out a while back, which is that we have very large interclass imbalances. So if you look at the categories for each of the halves of the spectrum, some categories of images are entirely missing from the upper half of the data set. So there, for example, no Leon curves, that's that are hard. I guess Nuremberg is a dog breed, but I could be wrong, don't quote me on that. And there are none of them in the upper half, so all of them are easy. Well, that's a problem because the network, instead of learning to distinguish image difficulty, is instead learning to just distinguish classes. It's just learning to say, if I see Leonberg, it must be the lower half of the data set, which is not too interesting. And then the same thing follows for the 5 category case. We also have very large imbalances there, although less exacerbated. So now I try to balance the data set, and these are the accuracies that we get when we try to distinguish images that are equally represented within the 2 parts of the data set, within the difficult and within the easy one. So we get above chance accuracy again. It decreased substantially, but it's still above chance, which is interesting. And the same goes for the 5 category case. So instead of splitting the spectrum in 2, we split it into 5. We again get above chance accuracy over here. Can we use training heuristics to predict image difficulty? So that was some steps we planned with David, and so here are the results, and I'll just explain you the idea here. So, how to use training heuristics for predicting image difficulty? Here's the question. So, take a misclassified image. So take an image that is classified wrongly, okay? And then only on that image do gradient descent until you get it correct. And just record the number of steps in gradient descent that it took you to get that image correct. Then reset back the weights to the original, so just pretend you didn't learn anything, and do that for the next image as well. So it's just a measure of distance, like how far from the current state of the weights is getting this image correct. So it's like this measure, right? And how does that correspond to image difficulty? Well, it turns out quite well. So tried a few models, and we got certainly statistically significant correlation. You see that the images that took the largest amount of steps to get correct are indeed on the macro level the hardest. So not the hardest only for this model, they're the hardest for all models, which is interesting because now you can use this to make predictions. If something takes a lot of steps to get correct, it is a hard image for all models, not just for the one that you're using to make the prediction, which is an interesting finding. The second idea was a similar measure, but instead of counting steps, we're accumulating loss. So we compute the loss that we get from misclassifying an image, and we accumulate it until we get to essentially loss of 0, or within an epsilon, 0. And that's another measure of distance that we can measure until we converge. And then again, we reset the weights to 0, and we see how that corresponds to image difficulty. The answer is that also corresponds to image difficulty. The higher the loss, the accumulated loss, until you've got an image correct, generally, that means on the macro level, the image was harder. And then the last measure we tried is essentially weight distance until correctness. And I'll just visualize this right now. So suppose that your network is here in the weight loss landscape, right? Then you're taking an image from the Q1, which is the easier half of the data set, and you're just optimizing to get that image correct from Q1. And you measure the distance between the initial weight vector and the final weight vector when you got that image correct. Then you do the same, but for a Q2 image, and you measure that distance as well. So can we say that the distance y is in general larger than the distance x, given that the image Q2 is ranked as more difficult than image in Q1? Yes, turns out we can. So the distance in the weight landscape from the origin is highly correlated to the difficulty of the image. That's actually the best predictor. So that we got the highest correlation there. Shout out to David. He suggested that as the cleanest approach. And yeah, so that's quite interesting. And what are the key takeaways here? Well, learning macro level dynamics is possible to do better than chance, even with a network, without training heuristics, just with a network. But if you use training heuristics, you can certainly do it too. And that's interesting because training heuristics seem to extend beyond just the local model. They seem to hold for many models. They're good predictors for the micro level dynamics. Future directions of where to take this, well, we're going to keep working on this. We're going to see how it goes with LLMs. I think it will go well, and how it scales with other data sets. And yeah, that's about it. Thank you guys, and thank you Brian, David, Magni. Shout out to you guys and to everyone in the Summer School. Yeah, it's been great having you all here.